Namaste children. Let us begin with Unit 6 Chemical Thermodynamics. Energy is one of the important factors which has significant contribution to our living standards. The three primary sources of energy, as we all know, is solar energy, nuclear energy and chemical energy. And the main focus of our discussion in this chapter is on chemical energy. We all know that almost all the chemical reactions are associated with energy changes. The energy change accompanying a chemical reaction is more significant than the reaction itself. For example, liberation of heat energy during the burning of coal is more significant to a common man than the production of carbon dioxide. Thermodynamics literally means conversion of heat into work and vice versa, because therm refers to heat and dynamics refers to movement. But nowadays the term thermodynamics is used in a much wider sense as it deals with almost all forms of energy. So thermodynamics can be defined as the branch of science which deals with the quantitative relationship between heat and other forms of energy. When we confine our study to thermodynamics of chemical process, it is referred to as chemical thermodynamics. Thermodynamics is primarily based upon three fundamental generalizations which have been arrived purely on the basis of human experience. These generalizations are called the first law, second law and third law of thermodynamics. There is also a zeroth law of thermodynamics which we'll be learning in this chapter. These laws of thermodynamics apply only when the system is in equilibrium or move from one equilibrium state to another equilibrium state. A system in equilibrium means the rate of the forward and the rate of the backward reaction is taking place in the same rate. Then you say that system is in equilibrium, which you'll be learning in detail in the next chapter. So in this unit actually we'll be learning some important aspects of thermodynamics. That is, we'll get an answer to the questions like what drives the chemical reaction, why the certain reactions are taking place only in one direction, what is the feasibility of a reaction at a given set of conditions, that is, why the reaction is taking place, what are the conditions for the reaction can take place, the feasibility of a reaction is the second one. What is the extent to which a chemical reaction can proceed? So you will be getting the answers to all these questions in this chapter. So let us go to the introduction part first. Here we must improve the efficiency of the engine. That's a picture given here. So as I told you earlier, branch of chemistry which helps to improve the efficiency of an engine is thermodynamics. So thermodynamics is a branch of chemistry which deals with the energy transformations of macroscopic system. I had defined the definition of thermodynamics earlier also. It is not concerned about the kinetics of energy transformations. Laws of thermodynamics apply only when a system is in equilibrium. That's what I told you earlier. When a system is in equilibrium or moves from one equilibrium to another. The basic definition. So before going into the details of thermodynamics, we have to learn first. As I've told you earlier, there are three important laws in thermodynamics. The first law, the second law and the third law. First law deals with the equivalence of different forms of energy. That is, energy of a system is conserved, which we'll be learning in detail. Second law deals with the direction of the chemical change, that which direction the reaction is taking place. If you're taking the reactants and products, reactants in a closed container, and the reactant is getting converted to products, we cannot know that whether it is going in the forward reaction or the backward reaction. So you will get to know in detail about the direction of a chemical change from the second law. Third law helps to evaluate the thermodynamic parameters like entropy. So you will be learning what is entropy in the second law. So this is what you're going to learn. So before going in detail, we should learn some thermodynamic terms, some basic terms and concepts of thermodynamics is very important before you go into detail of thermodynamics. So what are the first and the second term that is shown here on the screen? It is system and surrounding. So very easy term. What is a system and what is a surrounding? Let me tell you what is a system and surroundings before I go into this part. A system is defined as that part of the universe which is under investigation. For example, if you are interested in investigating the neutralization of sodium hydroxide and HCl, the solutions of sodium hydroxide and HCl constitute the system. That is, whatever we are studying, that will be the system. So let us go. See, system is a part of universe, which spelling is wrong here, part of the universe which is under observation or which is under investigation. You can see here that person is studying studying about a particular reaction, maybe studying about a particular reaction or something else. So whatever he is concentrating on, that is called the system. Then what is the surroundings here? The part of the universe other than the system is known as the surrounding. As I told you earlier, if you are doing an experiment, whatever experiment you are doing, that is the system, and all the other surrounding it is called the surroundings. From the name itself it is clear. The remaining part of the universe other than our system is known as the surroundings. Types of system. There are three types of systems. Systems may be classified into three types on the basis of movement of matter and energy in and out of the system. That is, based on the movement of matter and energy, we can divide into three types. So what are the three types? So let us see here. There is the system 1 here, and we are going to add matter into this beaker. Matter is being added, can be any liquid is added into the beaker, and we are going to heat it. So there is the energy, is there, matter is there, and the matter, whatever it is getting converted, the liquid is getting converted into vapor, and that vapor is called the matter. It is escaping out. You can see the beaker is kept open. It is escaping out. The energy is also escaping out. All the heat is going out because it is not kept closed. Now here they are asking us to cool. We are cooling it. So that is, the burner is removed there. Now remove matter. The matter is removed. You can easily remove the matter, right? Because it is kept open. So that is the system 1 shown here. So in the system 1, you can heat or cool the system. Heating and cooling the system is possible. Can add or remove matter because the beaker is kept open, so matter can be added also, matter can be removed also. That is, system can exchange energy and matter with the surroundings because it is kept open. Such systems are called as open systems. So it is very easy. A system which can exchange mass as well as energy with the surroundings is known as an open system. You can take another example also. Heating of calcium carbonate in an open vessel. Take calcium carbonate and heat it in an open vessel. In this case, heat is supplied to the system by the burner while carbon dioxide escapes into the surrounding. So calcium carbonate giving calcium oxide plus carbon dioxide. When it is kept open, the carbon dioxide formed as a product can escape out. So energy also can escape or matter also can escape. The second one, system 2. System 2, there the beaker is closed. You can see here the beaker is kept closed and there is matter inside it and heating it. So the burner is the starting energy. So you can see here the matter cannot escape out because it is kept closed. But the energy can escape out. So energy can be exchanged with the surroundings, but matter is not possible to go out because it is kept closed. Cool it. Remove the burner and you are cooling it. Add or remove water. What can you see there? Matter cannot be removed because it is kept closed. So in this system 2, can heat or cool the system. That is possible. Cannot add or remove matter because it is kept closed. system can exchange energy. System can exchange energy but not matter. There's a mistake there, children. System can exchange energy but not matter. Such systems are called closed system. So defining it once again, a system which can exchange energy with the surroundings but not mass. Look at the screen there. It is NOR given there. There's a spelling mistake there. Not matter or not mass is called a closed system. Next, we can see the next system is system 2. In system 2, you can find in this hot water, it's kept in a thermo flask. You know how it is when you're keeping water in a flask, thermo flask. The energy cannot escape out to the surroundings. Also, the matter is also remaining inside. So, both matter and energy cannot escape out. So, here the first point written here is cannot heat or cool the system. That is not possible. Cannot add or remove matter. You cannot add or remove matter. System cannot exchange energy and matter with the surroundings. Such systems are called isolated systems. So repeating it once again, a system which can neither exchange mass nor energy with the surroundings is called an isolated system. A reaction, an example, as I've told earlier, reaction carried out in a closed, well-insulated container such as a thermo flask. So there, if you're taking, for example, calcium carbonate, in a thermo flask, the vapor, that is carbon dioxide form, cannot escape out. Also, the energy is also not able to escape out. So, such systems are called isolated systems. Next important term, we can see here the state of a system. So what is the state of the system? This is another important term. That is, we have learned system, what is a system, which is what is a surrounding. We have learned the 3 different types of system. The next important thermodynamic term is the state of the system. State of the system refers to the conditions of existence of a system when its macroscopic properties have definite values. Once again repeating it. The state of a system refers to the conditions of existence of a system when its macroscopic properties have definite value. So, what are macroscopic properties? That is a system containing a large number of chemical species, that such as atoms, ions or molecules are called macroscopic properties. And the properties of a system which arise from the collective behavior of a large number of species are called macroscopic properties, like pressure, temperature, volume, surface tension. These are called macroscopic properties because they arise from the collective behavior of a large number of species. For example, in order to note the temperature of water, we do not deal with the individual molecule because the temperature is rising because of the kinetic energy, increase in kinetic energy of the whole molecules. It's not because of just one individual molecule. So such properties which depends upon the collective behavior of a large number of species are called macroscopic properties. So that is what I told earlier also. System, state of a system is refers to the conditions of existence of a system when its macroscopic properties have definite value. So it will be clear here. You can see here this is a system here. It can be hot something, tea, it can be tea or a coffee or hot water. It's written here, sorry, 50 ml of tea is written here. And this is at 1 atmospheric pressure, ordinary pressure. And here the temperature is shown here. Temperature is 94 degrees Celsius. So it is 94 degrees Celsius. The temperature is there. Condition is fixed there. It is 1 atmospheric pressure and the amount is also fixed there. Okay, so this hot tea is staying at 1 atmospheric pressure, the temperature 94 degrees Celsius. So the properties are fixed here. So the state of a system described by its measurable properties. A liquid can be cool. It can the ice is existing at 0 degrees Celsius. So there the conditions are there. Water can exist in the solid form at 0 degrees Celsius or below that. So that is a condition, that is a property at which that substance is existing in that form. So here the state of a system described by its measurable properties. There's a pressure, temperature and volume. These measurable variables depend only on the state of the system. These variables are called state variables or state functions. The state of a thermodynamic system described by its measurable or macroscopic properties. Such properties describes as state function or state variables. So this is simply you need to understand only the definition of the state of the function. State function and path function. The next important term is the state function and path function. Let me first explain and then we'll go to the screen part. The thermodynamic properties whose values depend only on the initial and final state of the system are called state functions. That is, these properties are independent of the manner as to how the change is brought about. The concept of state function, we can understand it, but let us take one example. If we consider h, small h, as the height between the top and bottom of the mountain, then h is independent of the path followed in reaching the top of the mountain. That is, you can reach the top of a mountain by many ways. There may be other long method, or you can directly go up to the mountain, but the height simply depends upon the initial and the final part. Hence, the parameter h is a state function. We call that is a state function. So, what is a state function, children? The thermodynamic properties values depends only upon the initial and the final state. It does not depend upon the path as to how we have reached that product. So here the examples of state functions are internal energy, enthalpy, this is another form of energy which we'll be learning in this chapter, pressure, temperature, volume. So all these are state functions. Now the heat and work that we all know, heat and work are not state functions, children. They are path dependent. That is, we know the work that we do. Whatever work that we do, there is no shortcut for anything. That is a usage that we have heard for many years. So the work that we do depends upon the path. It does not depend upon the initial and the final. So heat and work are not state functions because they are path dependent. So let us go through it. The thermodynamic properties which depends only on the initial and final state are called state functions. Example, internal energy, enthalpy, temperature, pressure, etc. We'll be learning the difference between internal energy and enthalpy. Enthalpy is also a form of energy, but what is the main difference we'll be learning in this chapter. The thermodynamic properties which depends only on the path followed are called path functions, and as I told you earlier, heat and work both are path functions and not state functions. Next is the thermodynamic properties. We'll go to the next one, thermodynamic properties. So here also again there's a 20 ml of tea. The mass is 120 gram. There's a temperature, it's at 94 degrees Celsius. And there is another cup there. The temperature is at 94 degrees Celsius. Both are same. Okay. Here the matter is less, I think. You're pouring this into the bigger one. So it becomes 30 ml. Total ml it is 30. Temperature is 94 degrees Celsius because both were at 94 degrees Celsius. The mass is 130. Thermodynamic properties. There are two types of thermodynamic properties, that is intensive property and extensive properties. What is intensive property and what is extensive property? That is what we are going to learn now. First we'll go to the intensive property. The properties which are independent of the amount of the substance added. The properties which are independent of the amount of the substance taken are called intensive property. To make it more clear, the properties of the system which are independent of the quantity or size of matter present in it are called intensive properties. And then what would be extensive properties? The properties which are dependent on the amount of the substance. That is, the properties of the system which depend upon the quantity or the size of matter present in it are called extensive properties. We'll go through the examples. Intensive properties, the examples are density, surface tension, temperature, refractive index, specific heat capacity, boiling point, etc. These are intensive properties. What are intensive properties? Which are independent on the quantity or size of matter present in it. Boiling point, as you can see here, it is an example of an intensive property. Why is it an example of an intensive property? Because it is independent of the quantity of matter present in it. The next is intense. There's a mistake here, children. It is not here. Second one is extensive property. Extensive property, properties which depend upon the quantity or size of the matter. Examples are enthalpy, internal energy, heat capacity, mass, volume, etc. Because mass and volume depends upon the amount of matter. When the amount of matter is greater, the mass will be greater. We know that. The volume also will be greater. Similarly, the internal energy also depends upon the amount of matter in it. So, all these are extensive property. There's a correction here. The second one is extensive property. Internal energy as a state function. Here you can find here internal energy is an example of a state function. So here a can is shown here. It is 1 liter of kerosene oil. It contains large amount of energy. It may be chemical, mechanical or any other type of energy. The sum of all these is the energy of a system. So, internal energy is actually the energy present in matter. And there are different forms of energy. There's internal energy can be, the molecules there is a vibrational energy. It's actually sum of many energies in internal energy. There is the energy of the molecules can be translational energy, rotational energy, vibrational energy, electronic energy, nuclear energy, etc. So internal energy actually is a sum of all these energies. In thermodynamics, we'll call it as internal energy. So it is simply the energy associated with a system. That is called internal energy. The sum of all the forms of energy associated with the system is called internal energy and it is denoted as U. A pan with water system has same amount of internal energy, has some amount of internal energy. A pan with water has some amount of internal energy, and here you are heating the system. So when it is heated, the system gains energy. The system is gaining energy. When it is placed on the table, the system will automatically lose energy. We all know about it. Similarly, internal energy varies. The first one, matter enters or leaves the system. So here there is one system which has internal energy U1 and there is another system which has internal energy U2. And U2 is greater than U1. Why? Because there is more matter in U2. Heat energy passes into or out of the system. So this is U1 and this is U2. System with the energy U2, heat energy is moving up. So U2 has greater energy than U1. So first one is matter is greater. Second one, it is having more energy after heating. Third one, work is done on or by the system. So here, one you can see here a container which move up with a movable piston. This matter has energy U1, and when it is compressed, that is when the piston is moving downward, the system's energy shown here, it is U2. It is being compressed. So here work is done on the system. In this case, work is done on the system. So the energy of U2 is greater than U1. So these are some examples. Okay. which of the system has high value of internal energy? Is very easy. There is A here 10 ml HCl, there is B here 20 ml of HCl. So whether it is A or B. Why? Because in B higher amount of matter is present. Second, you can find here there is 10 ml of water at 100 degrees Celsius and 10 ml of water at 30 degrees Celsius. So which is having more internal energy? The greater the temperature, more is the energy. So temperature of B is lower, so A will have higher energy. The third diagram shown here, a gas cylinder with 35 kg of LPG, and here it is 14 kg of LPG. So which will have greater energy? So here this is having greater energy because more of the matter is present here. So these are some of the basic terms of thermodynamics. Other than these terms, there are two other terms also which is not given here, which I am going to explain. It is reversible and irreversible processes. What is a reversible and an irreversible process? If you know what is a thermodynamic process, the operation which brings about the changes in the state of a system is termed as a thermodynamic process. And the thermodynamic process can be classified depending upon the conditions under which the changes are brought about. That is, there are, as you have learned in the states of matter, isothermal process is one thermodynamic process, adiabatic process, isobaric process, and isochoric process. What is isothermal process, which I had explained in the states of matter, but repeating it once again. It is a process which is carried out at constant temperature. That is called isothermal process. Adiabatic process. It is a process in which no heat exchange occurs between the system and the surroundings. Such type of process is called adiabatic process. A-D-I-A-B-A-T-I-C. Isobaric process. It is a process which is carried out at constant pressure. When pressure is kept constant, that process is called isobaric process. And last one, isochoric process. I-S-O-C-H-O-R-I-C. It is a process which is carried out at constant volume. That is called isochoric process. And other than these, there is a reversible and an irreversible process. So this term is very important, and it will be always this term is applied in thermodynamics. So what is a reversible process? It is a process or a change which is carried out infinitely slowly through a series of steps so that the system and the surroundings always remain almost in equilibrium state. The process is conducted in such a manner that at any moment it could be reversed by a small change. So any process which is carried out very slowly is called a reversible process. So we can take one example of a reversible process. Consider a gas enclosed in a vessel fitted with a frictionless piston. That is, a vessel is there inside which a gas is there. There is a piston also, and above the piston you can place some sand on the piston, placing a lot of sand on the piston, and your main work to be done is to push the piston, to expand the piston. That is, above the piston there is some sand kept, and you are going to remove each speck of sand. When you are removing each speck of sand, what is happening? The piston will move out slowly. That is, expansion of the gas is taking place. So you are removing each speck of sand, and the piston is moving very slowly upward. Its expansion is taking place. So just imagine removing one speck of sand every time is a long process, but this process is called the reversible process, because when you are removing a speck of sand, it is attaining equilibrium. The system and the surrounding is attaining equilibrium every time. So the reversible process is actually the best process, and the work obtained is maximum when it is a reversible process. It is a process which follows a reversible path, and this is actually an ideal process also. We know, we have learned slow and steady wins the race. So here in a reversible process also, this is the concept. But all the processes that we are carrying out are not reversible process. It is almost every process is irreversible process. It is only an imaginary process and cannot be done in actual practice. So then what would be irreversible process? A process which does not meet the requirements of reversibility is called irreversible process. That is, a process which is carried out randomly is called an irreversible process. Okay, so here work obtained is not maximum, and all the natural processes are irreversible process. Thank you, children.